Okay, so today we're going to be talking about postulates. And if you recall from our very first notes, there are five parts um, that we're going to be using during geometry. Okay, and so one of them was a theorem, and a theorem is something that can be proven. An axiom or a postulate is something that is true without proof. You don't have to, it's kind of the basics of why we know what we know, where it's like not why, but like essential things that are true. So 2 + 2 is 4. You don't have to prove it, it is true. And so as we look at these things, you'll notice these are things that we assume are true, and here's why. Here's kind of the rule that states these things. And we could use them in proofs. There's a couple we will for sure use in proofs, and I'll show you those. I'll have you star them. But most of them are just kind of assumptions. And so if you were doing a super formal proof, you might use them, but we're not going to do super formal proofs. We're going to just be doing like essential proofs to say, can we practice stringing together our statements so we can say, and therefore the result is these two triangles are congruent to each other. Okay, and so we're going to be doing essential proofs and practicing these procedures. So let's do a little review. Okay, so if you were in my class, I'd be like, okay, read these and fill in the answers from 1 through 8. Okay, so the process of observing data, recognizing patterns, making generalizations from your observations is called what kind of reasoning? That is inductive. If I could spell, that would be very helpful, but I'm struggling with that this evening. Okay. Inductive, okay. And you can't prove it with inductive. You can just show, hey, based on my sampling, this is what I've noticed. Okay. You can disprove it by saying a counterexample, but in general, inductive is just kind of noticing patterns and calling them out. Okay, the next thing would be a generalization made using inductive reasoning is called a what? A conjecture. And if I ask you to make a conjecture about something, you would say, oh, start with adding two negative numbers together. Guess what you get? Okay, the result is another negative number. Okay, so your conjecture is start with this is what happens. Okay, and then a what is needed to show that it's false? A counterexample. There is a way to show do inductive proofs, but you would not learn that until college. So we're going to hold off on that. There is a way. Okay. You prove it for n, and then you prove it for n+1, and then you say, okay, therefore, can we show that it works for all things? Okay. And so it's beyond what we're going to do in the scope of this class. So we're just going to say, is it true or false? If it's false, show me a counterexample to show why it is, or show an example of something that's not going to work. Okay. What kind of statement can be written as an if-then statement and consists of a hypothesis and a conclusion? That's a conditional statement. Okay, I could spell it right. O-N-A-L. Conditional. For example, if you eat your dinner, then you can get dessert. If you have a triangle, then it has 3 sides. Okay. Um, It's an if-then statement, and it has the hypothesis, which is the if part. Okay, don't use the word if. And then the then part, which is going to be the result. Okay. The process of using facts, rules, definitions, or properties to take a hypothesis and reach a logical conclusion. Okay, so you start with something and let's go to a conclusion. That is called deductive reasoning. Okay, so you're using facts, rules, definitions. That's what the lawyers use when they're like, hey, let's prove that my client is going to be innocent. Okay. And so we have a hypothesis. If this is true, and then the result, okay, get to the conclusion of nope, therefore they are innocent. Okay. Um, if you have this triangle, can you show that something about it? Okay, the result. And use deductive reasoning to get from an if to a then. Okay, a what is a way to deductively take a conditional statement and to link the hypothesis to that conclusion in a step-by-step manner using statements and reasons that are accepted true. In math, if you start with a statement, okay, and you link it step by step by step into the conclusion, okay, then what is that called? That is called a proof. Okay, if you start with two triangles, you can step by step show, hey, these two triangles are exactly congruent to each other. Okay, how? You do some statements and some reasons, okay? And you start with the two things and you end up with a conclusion. Therefore, it is by showing it by step. Okay. Postulates or axioms, we call them postulates pretty much in this course. Postulates are conditional statements that are accepted true without proof. Okay, they're basic principles. Okay, they're ideas about points, lines, and planes that can be stated as postulates. Okay. After a statement or conjecture has been proven true, it is called a theorem. Okay, so things that can be proven, okay, the Pythagorean theorem, you can actually prove it, okay, and it has been proven true, and you could prove it to yourself, okay. The Pythagorean theorem is something that can be shown to be true, okay. Postulates are those that you don't have to prove, okay. Theorems can be proven if you choose to, okay. And a theorem can be used in a proof, okay, as a reason why something is true, okay. And so you can use theorems as reasons as well. So you can prove them yourself, but you can also use them in your proof to kind of justify other things because somebody proved them before you did. Okay, so you can use them yourself. Okay, so postulates that are true that you don't have to prove them and you could use them in your proof. We don't normally do that, but let's talk about what they are. And we will be working with them on your homework today. Be like, why is this true? Because of the line postulate. What's the line postulate say? A line contains at least 2 points. Another way to say it is through any 2 points, you can draw just one line. Okay, so you start 2 points determine a line. Okay, and that's called the line postulate. Okay, and we can restate that is one line. Okay, so you can only draw one line through any 2 points. There's not multiple ways to do it. Okay, that's the line postulate. And now, of course, every line has infinitely many points on it, but 2 points are what you need to show the path of a line. The plane postulate, okay? Any 3 not collinear points. Again, we talked about if you want to talk about a specific plane, the 3 points have to make a triangle and then only one specific plane will rest on it. So through any 3 not collinear points is exactly one plane. And on every plane has infinitely many points, but 3 determine its pathway. Okay. The flat plane. Planes are flat. Okay. So planes are flat. Okay. And so if you've got a plane and you got 2 points on it, then guess what? The line that holds those points will be also on that. It's not going to be like a basketball where like, just because you've got a ruler that sits on a basketball, that one point touches the basketball, the rest of the points are not on that. Okay, no, we have a flat plane. So if there's a ruler on a table, it's going to be in that plane. Okay, all the points on the ruler will be on the plane. Okay, so if 2 points are on the plane, then the entire line is on it. So again, you can see we're going to use these as reasons today on your homework, but we won't. They're not that complex in terms of saying we're going to have to make a big deal about these. These are just true. You don't have to prove it. It's good for you to know them. Intersecting lines. How do 2 lines intersect? If they do, if 2 lines intersect, oopsie, if 2 lines intersect, they would intersect at a point, just one. Okay. If they're straight, lines are always straight. Okay. So if you have 2 lines and they touch each other, they're going to cross in just one point. Okay. Unless they're the same line, and that's a whole different story. But if you've got 2 different lines, the only way they can intercept, unless they're parallel, would be at one point. Okay. Intersecting planes. How do 2 planes intersect? Well, 2 planes intersect at a line. Okay. Think about the edges, the walls of a room. They meet at a line. So if 2 planes intersect, yeah, planes can be parallel. Like your ceiling and your floor, you hope they don't meet ever. Okay. But the 2 walls of a room, they should meet at a line. Okay. So if 2 planes meet, they should meet at a line. Now here's something we will use quite a bit. Okay. And so let's put a star next to it. I'm going to make mine yellow. Okay. The midpoint theorem. What's the midpoint theorem say? Now, somebody proved it, and we're not going to prove it this year. Okay, so you could prove the midpoint theorem. But basically, if you have a midpoint on a segment, guess what? The 2 parts of the segment are congruent. We've used the midpoint theorem, haven't we? If you know this is the midpoint, what do you know about these two segments? They are congruent to each other. So if you're like, why are these two segments are congruent? Why? The midpoint theorem states that. Okay, so if you have a midpoint, then the two pieces are going to both be congruent. Okay, so shapes can be congruent. Shapes cannot equal a number. Okay, I am not equal to a number. My feet size is a number. Okay, but I specifically am not. My age is a number, yes, but I am not a number. Okay, so shapes are not a number. The length of my feet, the length of, a building could be a number, but um, lengths could be equal to each other, equal to a number, okay, because they are numbers, but shapes could be congruent to each other. So there is a definition of a midpoint, and it's shown there. If you have a midpoint, then the two parts are equal in length. We don't really use that so much this year, but it's true. Okay, midpoint theorem is mostly what we'll look at, and so let's just focus on that. Otherwise, kids kind of get confused. They're like, when do you just use the midpoint theorem? If you have a midpoint, the two parts are congruent. Okay. Theorems tend to talk about the congruency of shapes. Okay, that's another good thing to know. Okay. All right, another thing we're going to be talking about would be the definition of congruence. Okay. There's a congruence theorem. We really don't use it. Okay. It's stated there. But the definition of congruence, we will use a ton. Okay. So put a big old star. So we'll use the midpoint theorem. We'll use the definition. What's the definition of congruence? Well, if two shapes are congruent, they have the same shape and size, right? That's what's going on. But what we'll use is this. If two segments are congruent, then their lengths are equal, and vice versa. If the lengths are equal, then the segments are congruent to each other. Okay, so that is going to be the definition. It goes both ways. It's a biconditional. Okay, equality of the length is it means that the segments are congruent, and vice versa. Okay, so that is going to be something we talk about, going both directions. Okay, the definition of congruence. Okay, so let's talk about which postulate or theorem will help us justify this. Okay, lines R and N intersect at point D. You don't even have to look at the picture. If two lines intersect at a point, what postulate do you know? Okay, it's the intersecting lines postulate. Read it. I can't spell right this second, but you can copy it from back here. The intersecting lines postulate states that if you've got two lines and they happen to intersect, how do they meet each other? At a point. They don't meet each other at like a social, they meet each other at a point. Okay, so how do two lines intersect? As a point. Okay, plane P contains some points. Okay, so my question is this: what postulate says that planes contain at least three non-collinear points? That would be the plane postulate. Any plane contains three nonlinear points. Okay, and that determines which way it goes. Any line starts with 2 points, but it'll have infinite. Okay. Planes P and Q intersect at line AD. Okay. Well, that's the intersecting lines. Nope. Planes. What do you mean? When planes intersect, if they do, how do they intersect? They make a line. That's what they do. Okay. And so, like, if you're talking about how do lions interact when they meet each other? I don't know. There's probably some lion journal that tells you what happens, but we know when two planes intersect, what they do is this, they make a line. Okay, next part. We've got, is this always, sometimes, or never true? And then show me why. Line R contains only point P. Well, that might be the only one that's labeled. And that is never true. Why? Infinitely many points are on every line, okay? Lines. Okay. Line postulate, I'll tell you how to say it. The line postulate says at least 2 points. Well, the truth is, the line postulate says it starts with 2 points, but then there's going to be infinitely many, aren't there? Okay. 2 points determine the path of a line, but then there'll be infinitely many points on it. Okay. Through points H and K, there is only one line that you could draw, and that is always true. And what I would say is this: if you cannot even think of one exception, if it's 100% true, no exceptions, then it's always true. If it even is 99% true, that's sometimes. Okay, it doesn't have to be 50-50. And then never means it, I don't even think of any one example that would work. Okay, so points H and K, there's exactly one, and that would be the line postulate. 2 points determine the path of a line. Okay. If two coplanar lines intersect, okay, so they're on the same plane and they intersect, then the point of intersection is on the same plane as those two lines. That would be always. So they're thinking, take a piece of paper, and if there's 2 lines on it, and if a line's on it, that means all the points are on that plane. And then if another line is on it, that means all their points. So if you take a piece of paper and you just draw 2 lines on it, every point that you've drawn is on the same sheet of paper, the same plane, and including the place where they intersect. So that's always true. Okay. And then we could call that, I believe that's going to be the flat plane postulate. Okay. That means if let's see what it says. Let's go back and read it. The flat plane postulate says if 2 points are on the plane, then the entire line is also on the plane. Okay. And vice versa. If an entire plane's on the lines on a plane, then every point is as well. Okay. So we're not living with a like a basketball, where 1 point of a line can be on the plane. So if you got a flat surface and you got a ruler on it, all the points on the ruler are going to be touching the plane. Okay. 4 points are non-collinear. That would be sometimes. Can you think of 4 points that could be linear, all on the same line? Could you think of 4 points that are not collinear? You can't connect them with that. Okay. And so, um, all right. The intersection part is a yawn. The intersection of 2 planes is a point. No, it's a line. That's never. And that would be the intersecting planes postulate. And I think you could show example of these 4 lines are collinear. And then these 4 points are not collinear. Okay, so you can give an example. Okay. Now we're going to talk about doing a proof. Okay. The proofs we do today are a little lame. I'm just not going to lie. But basically, you're going to start with some given information. And as we set up here, if you're going to be doing a proof, we're going to take a conditional statement and you're going to show if I have this, okay, then you're going to show that the result is true. Okay. So, and we're going to show it by step. Okay. And you can prove lots of things, including theorems, but we're going to show a couple things here. So if you have this, okay, then what we're going to show is then we're going to say, then you have that there. Okay. So the hypothesis is the given, the then is the conclusion. Okay. And so let's talk about if I know that Q is the midpoint of PR. So we can make a picture as we want to. If Q is the midpoint of PR, can we show that these 2 segments are congruent? Well, we know they are, okay? And that's going to be the, let's talk about how we would walk this direction, okay? And so how about, then we're going to basically show the midpoint theorem. Okay. We're like, hey, if you have a midpoint, guess what? The 2 parts are congruent. Why? The midpoint theorem. And if you did that in a proof, that would be perfect there. We're just trying to show the midpoint theorem right here. Again, I'm not going to make you do any proofs about exactly like this, but I just want you to see what is the deal here. Okay. Okay, if Q is the midpoint of PR, that's given. Okay, so why can I say it? Because it's a given. That's the if part. Okay, well then the result is that hang on a second. This should not be here. Okay, that should be your, we're trying to prove that PQ is congruent to PR, then that should be your last thing. So this should be, let's move this. Your last statement is PQ is congruent to QR. Okay, what we're going to say here is okay, so I'm going to do this and it's going to be a little bit kind of convoluted and I won't ask you to emulate this, but the truth is if you go back up here, Q is the midpoint of PR. Okay, so what does that mean? Let's go back up here. If you have a midpoint, there are two things you can do. You can say the midpoint theorem where the two segments are congruent, but that's what we're trying to show. So let's use the definition of a midpoint. Okay, so let's use the definition of a midpoint, which says if you have a midpoint, then the two segments are equal in length. Okay, so this is a little weird, but we'll just kind of go with it for right this second and say we'll do different things when I ask you to do them by yourself. So the definition of a midpoint. Okay, and then here's one I will ask you. If you know the two segments are equal in length, okay, what will let me say if they're equal in length that they are congruent and vice versa? This is something you'll use a lot, okay? This goes right up here, okay? The definition of congruence. If two segments are congruent, you know that they're equal in length. If they're equal in length, they are going to be congruent, okay? So equal in length means they're the same length, like numerically. If they're congruent, they're the same shape and size. Okay, so if they are one, they got to be the other. So we would say definition of congruent segments, which states if you have congruent segments, then their lengths will be equal, and vice versa. If you have segments that are equal in length, they will be congruent. So that shows that, hey, guess what? I have a midpoint. That means the lengths are equal, and then that means since equal lengths means congruency, therefore, we've shown our if-then statement. Okay, so we're just kind of walking into the situation. Okay, here's another one. If B is the midpoint of AC, okay. So B is the midpoint of A to C, and then C is the midpoint of D to E. We want to show, okay, that AB and CE are congruent to each other. That's what we want to show. You're like, well, we know it's true, but if we have this, then can we show this right here? Okay, so we're trying to get from the if to the then, this, the hypothesis to the conclusion by a step-by-step deductive proof. Okay, so let's start with stating our givens. We know from the proof, okay, we got to state it here like a court of law. Given this, we know we've got some midpoints. And since we've got two statements that have the same reason and they're kind of very similar, we're going to put them in the same step. So given. And so if we know this, is there another thing that we can call out? Okay. So we know these two givens, and sometimes people check them off to be like, did I use them both out? Okay. And we also know that A, B, and CE are equal in length. Okay. So that's another thing that we're given. So and again, I kind of breaking my rule. Definition of midpoint. What does the definition of midpoint say? It says that that if you have a midpoint, their parts are equal in length. So we can say that AB equals BC, and we can say that DC equals CE. Okay, so we're going to use the definition. We really won't use that so much in general, but we're going to use it today. Okay, and then therefore AB equals CE. How do we know that? Well, look at the top. That actually is another given feature. So we know that is a given. So because we have midpoints, okay, we know we can call out step 2. Okay, so we made that step ourselves, okay, because we know the definition of midpoint states the parts are equal in length. And then we are also given that A, B, and CE are going to be equal in length, okay? Okay, so we're given that. What we want to prove, I misspoke earlier. We want to show, okay, that BC is going to be equal in length to DC. That's what we want to show. We know that the other two parts are equal. Okay, and we can kind of see that's got to be true. Okay, and so the next thing is that what can we do next? Well, we are going to kind of put step 2 and 3 together. Well, step 2 and 3 is going to say if AB equals CE, okay. Trying to see how we want to actually show this visually. Sorry. Let's go to this up. We're going to state that BC equals CE. Okay, let's see why. Okay. We're going to do like a substitution type thing. Okay, it's actually the transitive property. Okay, we're going to call it substitute for a second. Okay, so we're going to use this. And what that means is that substitute things that are equal to each other, okay, in this problem. So since AB equals BC and AB also equals CE, okay, well, let's put this with this and say if AB equals BC and AB also equals CE, well, we know that BC has to equal CE. Okay, so AB equals both BEC and CE, so therefore they must be equal. Okay. And then the next thing is going to be, since we know that BC and CE, let's look at this part right here. Since we know that BC equals CE, instead of CE, we can put DC. And so therefore, this must be true. So we did some substitution. It's called the transitive property for real. But we notice that if we know AB equals both BC and CE, well, we know that BC and CE must be equal to each other. Also, if we know that CE also equals DC, we're going to take DC equal to BC and put that down here. So we're taking some steps, and I don't expect you to be able to emulate this at this point. We're noticing, we're trying to say, can I get from the ifs to the thens? Can I get from the statement to the conclusion? Okay, can I get from the hypothesis to conclusion? All right, so we'll take some steps together and keep on trucking.